We're going to review some ideas from chapters 1 and 2 and also begin to connect those two ideas that we have within chapter 3. When we've looked at how we can improve our understanding and recall of information, it's important to recall information from our long-term back to our short-term memory and make connections. I also find it helpful to be able to summarize information. If we have a lot of different sources, to consolidate that, generating our own understanding. In a way, what we're doing in that process is we're taking information from our own long-term memory and bringing it back into our short-term in order to use it. So within this video, we're going to do that and connect it to new ideas as well. So we introduced last time the idea of combustion reactions. That's one type of reaction. Decomposition and combination reactions are other ones. One good resource to point out for you, at the end of the chapter, within the e-text, before the problems show up, there's a summary for the different sections. This can be a helpful way to review. So if we look at the summary for section 3.2, we find that there's different types of reactions listed: combination, decomposition, and combustion. Combination reaction is with two or more reactants combined to form one product. Decomposition is when one reactant breaks apart to form two or more products. And a combustion is a specific one, reaction with oxygen to produce carbon dioxide and H2O. So this idea of being able to balance different reactions, this is one that I ask you to give a try. Let's connect it to those other ideas. So at the top here, I see two examples of combination reactions. Let's extend that and put those into words. Carbon monoxide gas reacts with oxygen gas to form carbon dioxide gas. Or dinitrogen pentoxide gas reacts with water to form nitric acid. Aqueous nitric acid, aqueous, that symbol AQ means it's dissolved in water. So the symbols we might see there would be solid, liquid, gas, or aqueous. Silver 1 oxide decomposes into silver metal and oxygen gas. This is an example of a decomposition reaction. If I were to balance that, those would be my coefficients. If I were to look for a combustion reaction, that last one is a combustion reaction. This idea of being able to consider things as the formula that becomes a balanced chemical reaction that we can discuss within word description, connecting to different types of reactions, all good skills that we want to have. Working through this part, these involve different ideas. They're all combustion reactions, so let's look at the first one. Propane is involved in a combustion reaction. So right away, I'm going to take propane, 3 carbon atoms, 8 hydrogen, reacts with oxygen to form CO2 and H2O. The simple organic molecules we want to know are these single carbon chains: methane, ethane, propane, butane, where we're changing the prefix there to tell me how many carbons are present. To balance that, I'm going to leave the oxygen for last. I'll start with a 1 in front of my first molecule, and it works, so I can then just add a 5 for the oxygen. Total number of molecules of product for every 1 molecule of propane. 1 propane gives me 7 molecules of product. Hexane, another prefix, hex means 6, and we've got our carbon chain. I leave the oxygen to balance last. That's the case, though, when I get to this, I've got an odd number that's messing me up, so I'm going to double all of them to get rid of the odd and figure out how many oxygen molecules I need. This one's a little bit more complex. If 6 molecules of hexane were used, how much oxygen would you need? Well, the formula tells me 2 molecules react with 19. So we can set it up as a simple proportion. 2 molecules of hexane react with 19 of oxygen. So therefore, if I have 6, how much oxygen would I need? Cross multiply and divide tells me the number of oxygen molecules. I'm using the coefficients to set that up as a proportion. Methanol. Methanol is another simple organic that we want to know. So besides the carbon chains that have strictly carbon atoms surrounded by hydrogen, if we replace one of the hydrogen atoms by an OH, we've turned it into an alcohol. So with the same prefixes, we can now name methanol, ethanol, propanol, butanol, hexanol, octanol, etc. So this would be methanol, 1 carbon atom, and the instead of all hydrogens, one's been replaced by this OH group. To balance that, I would start with putting 1s in and see if that works. Led me to an odd number, so I had to double it and make it was 3 oxygen at the end. How many molecules of carbon dioxide are produced for every molecule of methanol? 2 produce 2, so 1 would produce 1. Simple proportion. If you produce 10 molecules of CO2, how much H2O was also produced? Just somewhat more complex, but let's look at our coefficients. 2 CO2s give me 4 H2Os. 2 CO2s give me 4 H2Os, so 10 CO2s would give me 20. This last one I think is the most advanced. So this says we start with 4 molecules of methanol and 6 molecules of oxygen. We put them in a container. They react as fully as they can. What are we left with? Try to make it a sketch at the particle level. So we have our balanced formula here, our balanced equation. I'm going to use this to represent the particles beforehand. So to help you see, I'm going to write what the formulas are. So I've got 6 molecules of methanol, 6 molecules of O2 gas. To also keep track, I'm going to introduce what's called a before, change, and after table. We're going to see this later within chapter 3. I just want to introduce the idea right now. So beforehand, let's just count up what's in our container. We had 6 molecules of methanol, 6 molecules of oxygen. We're going to use them up as fully as we can until we run out of one of them. We're going to find that that means we use up 4 of the methanol and 6 of the oxygen, because the oxygen molecules go all the way down to 0. After those go all the way down to 0, we still have some methanol left over. We have 2 molecules of that left over. So I've used the reactants and found that I could take one of them all the way down to 0, but it left some of the other one remaining. How about the product that forms? I found out that I've used up 4 molecules of methanol. That means I would form 4 molecules of CO2. The coefficients are the same, 2 to 2. So if I use up 4, I must get 4. If I use up 4, I must get 8 of the H2O, because the coefficient's twice as much. I'm just looking at the proportions there, and I'd figure out, okay, that's what tells me that I have as far as products forming. This skill right here, this brings together a lot of ideas, and this is one of the most high-end within all the chapter. We'll practice it more. So within this case, why do I say it high-end? It involved naming of methanol, knowing what a combustion reaction was, balancing the formula, doing an analysis of what's before and after, and including things that are left over. Really high-end question for us. Looking then at Avogadro's number, a lead into that is being able to calculate formula weights. This was one that was in a pre-class video. People did a really good job within this one. They were able to recognize that oxygen was in the 2- column. So when naming it, they needed to specify it as iron 3 oxide. Roman numeral 3 tells me it's iron 3 plus. For the formula weight, or the percent of the total mass coming from iron, we're using the periodic table for that. The idea of naming this is a naming an ionic compound. That's back from chapter 2. These were new skills for us, using the periodic table to look up the mass values and combine them to come up with the entire formula, or talking about a percentage. Those are new skills that we're going to be using in chapter 3. The units on this, AMU stands for atomic mass unit. What's an atomic mass unit? So I'm going to go back to chapter 2 here. We looked at symbols like this in chapter 2, where we wanted to make sense of what the superscript and subscript corresponded to. We also looked at these descriptions of charge and mass. The charge, that was in multiples of the fundamental amount of charge, the charge of an electron. How was the electron's charge determined? Well, for the early experiments, we want to know the scientist, the experiment, and the significance of it. This is associated with Millikan's oil drop experiment. He determined the total amount of charge different oil drops acquired, and from that, he determined the charge of a single electron. Within the video, people did a nice job of giving explanations for this. Most of the questions seem to arise involving what were the X-rays doing, and how did the step size mean something. The X-rays are being introduced into the chamber. They're ionizing the air that's in the chamber. They're transferring different number of electrons onto the oil drops. And then Millikan is determining that total amount of charge the drops have acquired. That's what then is used over here with the step size. He finds that they're varying by a set increment. That set increment is being explained by to go from one step to the next, you're changing the number of electrons. He's not controlling the number of electrons that are acquired, but he sees that they follow that set pattern, and that smallest step size, that's the charge of a single electron. Within the same table, notice the mass units are in AMU. So early chemists were able to determine the relative amounts of substances that reacted with each other. That's how they came up with relative mass values and found that hydrogen was the lightest atom. If we think back within chapter 1, we have some insight to the kind of experiments they might be doing. So they would take water, send electricity in, and found that it produced two new substances, oxygen gas, hydrogen gas, in different volumes. So these are the kinds of measurements they could make. We use this as an example back in chapter 1 of a chemical change. New substances are being formed. Water is a substance, and hydrogen gas and oxygen gas are different substances. Looking at this at the particle level, in this era, Dalton, with his billiard ball model, would say, okay, they're combining to form water. The actual analysis produced more H2O than Dalton would have thought possible. What was going on at the particle level? What did Dalton have wrong? He didn't recognize that hydrogen and oxygen were both diatomic molecules. If his same analysis was set up with diatomic molecules, then it gave the correct amount of product forming. This is what a scientist named Avogadro proposed, that they were being found as diatomic molecules. This wasn't well accepted because it seemed crazy. What did it mean to say the same particles would stick together? Opposites didn't seem to be attracting there. This whole setup right here, this historical context, not something that you need to know, but I'm using this to illustrate things you do need to know, which is which molecules are found as diatomic, and also how do we interpret these particle level diagrams. In AMU, if we figure out the actual mass for an atom, it's a really small amount. We typically will not be using those small amounts. We're going to be using a larger amount, a mole amount, which I'll talk about in just a second. This AMU unit scale, it's set up where the carbon isotope, carbon 12, is defined as having a mass of 12 AMU. Let's connect that to an earlier idea. So back in chapter 2, we looked at the operation of a mass spectrometer and saw that that would let our particles, they were formed into cations, and they'd have different pathways when they went through the magnet. And that gave us a ratio involving the charge and the mass. So here's some experimental data. If you test hydrogen in a mass spectrometer, there's a big peak at a mass of 2 and a smaller at 1. If I look at the periodic table, the mass of hydrogen is really close to 1. What's going on? It's that when it's going through, it's saying primarily the H2 molecule, and a very small amount is the actual hydrogen atom. Would that be consistent with these other samples like chlorine and hydrogen chloride? It would be. In this case, we have some fragmentation, so we see the isotope for chlorine 35 and 37. But how do we add up the masses of 70 or 72 or 74? It's because we have the molecules with the different isotopes. That's consistent as well here with HCl. Looks like in this one, to end up with masses of 35, 36, 37, and 38, it's a combination of the individual atoms and then the molecules as well. This relates to something that you saw in a Mastering Chemistry assignment, where sometimes within a mass spectrometer, it could be set up so you only get atoms, but frequently you get these larger fragments as well. This is not the case where I would expect you on a test to be able to predict, but given the output, I think you could work it backwards and explain what's going on and assign the different peaks. One other connection to make with our mass spectrometer, we also looked to see how this was related to the phenomena of if you have a charged particle, it will be deflected in the direction based on its charge. And the extent to which it bends, that depends on its momentum. A particle with a lot of momentum, let's say a large mass, large velocity, for the same amount of tug for the force, it wouldn't be deflected very much. Moving on then to Avogadro's number in the mole. We saw that the mass for a single molecule, very small amount. To take that to an everyday amount, a laboratory size, something that we could actually measure, we're going to take that, and instead of considering just one molecule, we're going to consider a mole's worth. A mole's worth is 6.02 times 10 to the 23rd of those. Avogadro's number's worth. So instead of looking at just one molecule, we're going to look at a mole's worth. 6.02 times 10 to the 23rd molecules. When we do that, the mass, instead of being considered AMU, it's going to be grams. Grams per mole is molar mass. We're going to be using molar mass a lot. Where did the value come from? I think it's cool. This is from Robert Millikan, his oil drop experiment. Notice how he's linking electrical charge with Avogadro's constant. I think it's great. This is his actual writing here. So where's this come from? These early experiments in the 1800s found that you could add electricity and turn sodium cations into sodium metal, magnesium cations into magnesium metal. They're like electrolysis experiments, but instead of breaking it apart, we're adding electrons here to form these metals. They were able to determine that the charge for the total amount of charge for this to take place, they found that it was a certain amount of charge per mole of electron, but they didn't know how many electrons were in a mole. They just knew that it added up to a certain amount of charge that they were using within their analysis. So within the oil drop experiment, Millikan determines the charge of one electron. Then he can set up a ratio and figure out how many electrons were there in that mole. So this is not a learning objective. This won't be on your test, but I think it's really amazing. This is where that value comes from. So when we look at how to use molar mass, you could consider having a mole of molecules. If you have a mole of molecules, you've got 6.02 times 10 to the 23rd of those molecules. You could have ions. You could have it for an ionic compound. If you look up an ionic compound, barium chloride, if you add up the masses of barium, chlorine, and chlorine, it'll get to 208.2. 208.2 what? Well, if you consider that to be a mole's worth, 208.2 grams. 6.02 times 10 to the 23rd of the barium ions, and then 2 times 6.02 times 10 to the 23rd for the chloride. If we want to make conversions between these, molar mass is really important. Molar mass is something we can look up at the periodic table by using the formula, and that allows us to go between grams and moles. This is a really important skill for us in Chapter 3 and beyond. To go between moles and the actual number of particles, we'd use Avogadro's number. We do this much less frequently. Using the molar mass, we use that all of the time. Here's a couple sample problems. If we have a certain number of moles, that's given the symbol MOL, a certain number of moles of cholesterol has a mass of 0.406 grams, what would its molar mass be? I find for this it's helpful to go back and say molar mass is grams per mole. You've given me a certain number of grams corresponds to a certain number of moles. So in grams per single mole, this would be the value. The second one here is a little bit more complex, and I'd use dimensional analysis for this. A sample of ethanol includes a certain amount of carbon. How many hydrogen atoms would be present? I'm going to start on the left-hand side the information that was given. 0.345 grams of carbon are in the sample. In order to cancel that, I need to have grams of carbon in the denominator. What do I know about grams of carbon? By looking at the periodic table, I know that 1 mole of carbon atoms adds up to 12 grams. If I then look at the formula for ethanol, I can convert from moles of carbon to moles of hydrogen, and then finally, using Avogadro's number, convert to how many hydrogen atoms I have. This is a more complex one, but with the dimensional analysis, I think it helps to keep track of what's going on. This bottom set here, definitely a learning objective for this chapter. Using molar mass, we're going to do that all the time. The second, more involved one that involves aspects of looking at the periodic table to get the mass and Avogadro's number, I think that's a pretty specific question for this part of Chapter 3. From the pre-class video, here were a few that were similar that you could work on. If we connect this back to good learning strategies, anytime you have an opportunity to write down and share your work, I think that's a good thing to do. And you can do that in Perusal. If you want, write out your work, upload a screenshot. That way you can make sense to yourself what's going on and make sense for other people too. When you come to questions like this, it's also really helpful to treat them as a self-assessment. ask, okay, did I have to look back for other things, or can I authentically try to solve this when I see the question? Either way, whether you looked back for more information or you tried to solve it, that's where your metacognition comes in. Were you able to solve it? Are these easy questions for you? Are they things you're able to explain? Have you reached 100% mastery? If not, I think you might need more practice. Another good thing to do is to analyze them. What do you think the most important step in the process is? What would be the most common mistake? So instead of just coming up with a number, analyze it a little bit more fully. Another good resource within your book, and this is on the same topic, are the worked examples. So here's a worked example within the book where the first step is, okay, let me analyze it and figure out exactly what it's asking. And then crucially, let me make a plan. The plan that it points to are these conversions between grams, moles, and formula units. When I see this question, what pops into my head right away, I'm going to have to look at the periodic table to come up with a molar mass. And if you're asking me a specific number of molecules or atoms, I'm going to have to use Avogadro's number for that. That's exactly what they're describing here too. When they work it through, they show the math of it. And this involves both steps, going from grams to moles, and then moles to number of actual molecules by using Avogadro's number, and then rescaling that. It finishes by saying, okay, check your work. I find within the checking step, this can be helpful to do without a calculator, or without a calculator where you plug in all of the parts. Sometimes we trust the calculator too much without stopping to think. I like the analysis here where it said we began with a mass that was less than a mole, so therefore it should be less than 6.02 times 10 to the 23rd. Excellent step. So if I know that a mole's worth is 10 to the 23rd and my answer is 10 to the 22nd, okay, it seems like I might be in the right ballpark. Another good strategy is when you're done, ask yourself, well, what would be the most common student error here? Pause, and that might give you insights to an error that you have actually made too. Also in the e-text after the worked examples, this is really helpful. If you follow through a worked example, there are follow-up questions, a self-assessment. Sometimes it's a little bit more conceptual, sometimes it's calculating something specific. These, within the work text, the combination of a worked example that you analyze and think about, and then your own self-assessment afterwards, definitely a good pairing. The idea of taking the question and then elaborating on it, that's another thing that you can do. What do I mean by elaborate? Can you take and change what was there and make a similar problem but ask in a different way? In this one, well, what if we went and ran it in reverse? A sample of ethanol contains a certain amount of hydrogen atom. What would be the mass of it? So I'm just trying to think about what was given, but change it around a little bit. So within this, what I've been talking about, we began by looking at different types of reactions. The key one to memorize in that would be a combustion one. We briefly looked at some math involving formula weights. This idea of converting from grams to moles and back and forth, really important skill. From number of molecules to moles, back and forth, using Avogadro's number. It's important in chapter 3, but it's not necessarily something we're going to be using again and again. Also, I've given us a little preview here when we were looking at these before, change, and after tables. That's going to be an idea that we use later on in chapter 3 when we're looking at the reactants that are used up and the products that are formed in a reaction. So where to next? At the end of the chapter, here's some good questions involving formula weights. It would be great to try to review the information first and then give these a try. See if you can test yourself. I also like the way that some of these don't give you the formula. Phosphorus trichloride, chromium 3 sulfate. Those are ones that you should be able to recall the formula and apply your understanding of that as well. In terms of using Avogadro's number, more practice. You can, in this case, once again, review first and then see if you can apply and get to the answer. For all of these, the ones that have odd numbers have their answers shown in the back of the book, or I think within the e-text, if you click on it, it shows you what the answer would be. And notice how they're paired. Questions 36, 37, same kind of skill, and so the answers for one set would be in the back of the book for you.